This is presentation 6 for Brianna, Jenni, Faris, and Michael, and during this presentation we will discuss a discrete event simulation problem. The discrete event simulation problem we selected has 2 help center desks taking calls and servicing 3 callers. Callers require help by length of time distributed exponentially with a mean of 1 over mu. For this call center problem, if both helplines are servicing a caller and the third caller is waiting for assistance, the rate at which this person will be helped equals lambda. Callers call independently of each other for assistance. MATLAB was used to construct this problem and to test and analyze. The main principle used was the Markov chain model. Each node in the Markov chain has different numbers of outgoing calls, as shown in the picture below. And the combined outgoing calls is found using lambda plus mu. The nodes created represent 6 different states. The first of 0 has no calls in progress with 3 callers waiting. The second is node 1 with 1 call in progress and 2 callers waiting. There are 2 with 2 calls in progress and 1 caller waiting. Node 3 with 2 calls in progress and 1 caller that is impatiently waiting. And node 4 has 1 call in progress and 1 caller impatiently waiting, and node 5 has 0 calls in progress and 1 caller impatiently waiting.
As we discussed before, we used MATLAB to solve this problem. We created a matrix and we called it Q. Then we combined the rates described above as shown on the diagonal for the matrix. In the matrix, each node in the Markov chain has different number of outgoing jumps. This is the code that we used. We first simulated the transitions and we changed the number of n different times to test the results. Then we simulated the current state during a specific time. After that, we determined to which state to transit to. Then we ran the code for the next round. How close our problem to reality? The problem that we used is exponential distribution, so we can predict the length of calls and arrival calls. This allows a discrete event simulation, but may not exactly represent a real day in a call center. The more runs, the more accurate it would be. We may find that this is not the best approach for simulation and changes could be made to the model. For example, we started with an n equals 50, then as we increase n to 100 and then again to 500, this gets our simulation results closer to analytical results.
After running the experiment, we can see that the first run using n equals 100 shows the graph on the left where the simulation results are pretty close to the theoretical. But when n equals 500, there is less experimental error and the simulation results are extremely close to the theoretical, showing that this seems to be a sufficient model for the call center problem. As you can see, the simulation experiments should be run multiple times to increase accuracy when we want the simulation to be as close as real events as possible. The graphs are very helpful to compare and create visuals for results, including comparing the simulation results with the mathematical calculations for comparisons. If it is available, use a data set to compare the simulation with to see how accurate it is to the real-world problem.
Because of the complexity of optimization problems, the objective function becomes difficult and costly to evaluate. Therefore, you need to develop the correct mathematical model to simulate. The problem should be solved iteratively to minimize computation time. With each iteration, the solution should become closer and closer to optimal. If there are too many possible input variables, find optimal values for input variables instead of trying all possible values. Then determine the input variables that change the solution the most.